Понятно. Так. We resume our seminar, which is called, as you remember, Algebras and Analysis. And we open our new year, I hope, of our seminar with the lecture of Norbert Tiborovich, now just Norbert. Life is, complicated. Nemeš, which is, how it is called, he will remind us. And please, Norbert, begin. We are, as French say, how do they say? Nous sommes tout oreille. So please begin. Okay. So, Norbert. Так. Invariants of space from everything. So please speak. Norbert?
Hello.
Yes.
Can you hear me?
Yes, I hear you, yes.
Can you see my screen right now?
Yes, invariants of space.
Okay, let's start.
Okay. Okay.
Today I'm going to talk about invariant subspace problem. It gained attention recently because of the publication of Per Энфло. He claimed that he finally solved that problem in his recent article from 24th of May, I guess. His solution is only 13 pages long, but I haven't seen any specialist claiming that this paper is valid. So I didn't try to read through the paper, and my talk will be just a short overview of the problem overall and a few details of the proof of different mathematicians on related results, a little bit of drama, and a few unsolved problems.
And,
so let's start.
Norbert, and what about other people? Did anybody say something already, or still not?
Well, I'm planning to talk a bit about this, about opinions on this matter.
Okay.
Okay, so the formulation. I'll give a purely algebraic and not so interesting formulation, and during the talk we shall add more and more details. So the original question looks like this. Suppose we have a vector space E, maybe a complex vector space or real vector space. Suppose we have a linear operator on E, and our question, does there exist a linear subspace of E, say F, such that T maps F into F? This relation is called an invariant. This subspace is called T invariant subspace. So our question, does an arbitrary linear operator admit an invariant subspace? Why is this question so important? The main reason is that once a specific class of operators admits a lot of invariant subspaces, one can expect a structure theorem for this class. The simplest example comes from the linear algebra. So suppose that E is a complex vector space of finite dimension. Okay, let's say that's an example. Suppose E is a finite dimensional vector space. If you know the structure of the lattice of invariant subspaces for a given matrix, for a given operator, you can expect the structure theorem. For example, if we are given a linear operator on E, and we know that he has the operator admits a chain of invariant subspaces,
Mm-hmm.
there exists a chain C
Mm-hmm.
of T invariant subspaces. Then T is has an upper triangular form. That's the first example. Another example, an operator T is similar to a Jordan block matrix,
Mm-hmm.
if and only if its lattice of invariant subspaces is a chain.
Mm-hmm.
Let of T is a chain. But all these results can be achieved without deep understanding of the lattice. We all know these structural theorems proved via simpler methods. But for the case of functional analysis, these talks about invariant subspaces gain more attention. For example, the understanding of invariant subspaces of normal operators on Hilbert spaces give us the representation theorem, the celebrated result by John von Neumann. He showed that every normal operator on a Hilbert space is equivalent to a multiplication operator on some measure space, on some Hilbert space represented on some measure space. Another example is compact operators. There is a theorem by John Ringrose. He proved it in 1962. And his theorem says that if E is a complex Banach space, T is a compact linear operator on E, then T has generalized triangular form. What does it mean? It means that T admits a chain of invariant subspaces.
Mm-hmm.
Chain of T invariant subspaces. And if we try to write down the matrix of this operator, it will look like a block upper triangular matrix.
Mm-hmm.
This is not an exact statement, because here I talk about infinite matrices. But you get the idea. We take these invariant subspaces F1, then F2, which is bigger than F3, and so on. And we can talk about the matrix on these subspaces. And the matrix will look like this. It will be an upper triangular block matrix. This results mostly based on the representation theorem of compact operators, of the spectrum of compact operators. As we know, every compact operator has a point spectrum, and the only point of the spectrum which is not point spectrum could be 0. That's the results that motivate our interest to the invariant subspace problem. Now let's go to the history of the question, but first we shall start from the simple examples like linear algebra. At this moment, we do not use any kind of norm or topology, just to give a motivation for the exact statement of the analytic version of invariant subspace problem. The first observation that the zero subspace and E are always invariant. That's obvious. So if you want to give a clear question, you need to say that the subspaces in question here must be proper subspaces. Another uninteresting example is linear spaces of dimension 1. So we exclude them also because if dimension is 1, then we know the lattice of invariant subspaces. It's just 0 and E. Okay, then what kind of examples can we expect in the algebraic case? The first, not so trivial, the first source of non-trivial examples are the image of the linear operator. It's clearly an invariant subspace, and the kernel. Hence, if operator is not injective or not surjective, we clearly have an invariant subspace. So in this case, we shall consider mostly bijective linear operators. Another interesting example is so-called cyclic subspaces. I shall denote them like this, where B is an element of E and probably it's not 0. Otherwise, the construction is not interesting. So the cyclic subspace is defined like this. It's a linear span of the vector V and all possible applications of T to that vector. Sometimes we shall consider tails of these subspaces, where we can take applications starting from some power of T, like N. And this is basically the building block of many examples and counterexamples in the theory devoted to invariant subspace problem. In cases where V sub T is the whole space, we say that B is cyclic vector. Well, now let's move to finite dimensional case. I forgot, we already have discussed the final dimensional case here. So let's go to the case where dimension of the vector space is infinite. In this case, we have two options. The first option is when the dimension of E is huge, like uncountable. Then we can find an invariant subspace for a very simple reason. The cyclic subspace of any operator will be at most countable dimension.
Yeah.
Hence, it's a proper subspace. Problem solved. The more interesting case comes from the linear spaces of countable dimension. In this case, we can consider a tail of some cyclic subspace. One of the tails definitely will be a proper subspace. And then the problem solved again. So there is nothing more to add for pure linearly algebraic case. And now let's move to the case of vector space with topology. The most interest for this problem comes from the case of Banach spaces. And during my talk, I will mostly consider only Banach spaces here. So from now on, we require that E is a Banach space and T is a continuous linear operator. Let me add here analytic case. We need to consider complete topological vector spaces, and in case of normed spaces, it's Banach.
Yeah.
E is continuous. And I think that is all. As for the infinite dimensional case, we need to give a few observations here too. The first observation that T must be a linear isomorphism because it's an algebraic case. In algebraic case, T needs to be a linear isomorphism. But for the spaces with topology, we can have some problems with dense subspaces. And that's the reason that we shall use closed subspaces instead of just linear subspaces when dealing with invariant subspaces. Let me give this observation here. The first observation, suppose that we have a continuous linear operator on a Banach space, and in this case, the cyclic subspace will still be an invariant subspace. It will be a proper subspace of the Banach space E. Why so? For one simple reason. The subspace of a Banach space cannot, the closed subspace of a Banach space cannot have a countable dimension. This is a consequence of bare category theorem.
Yeah.
In this case, this gives the motivation why we need to consider closed proper subspaces in analytic version of invariant subspace problem. Let me use an abbreviation for invariant subspace problem. In what follows, I shall say ISP.
Mm-hmm.
Now, let's formulate the ISP as it usually done in textbooks. Suppose E is a Banach space, T is a bounded linear operator. The question is, does there exist a closed subspace of E, proper closed subspace, such that T of F is a subset of F? This question in the Banach space can be easily solved for non-separable Banach spaces.
Yes, of course.
If E is not separable, then the closure of the cyclic subspace is always a proper subspace, because this closure will be separable. It's a closure of the linear subspace of countable dimension. So ISP is resolved here. The only interesting case then, the separable Banach spaces. This is where we need to implement all our crazy techniques of the last 80 years. Not 80, I think already 100 years.
Yeah.
So the history of the question now. This will be a long list of different results and a few comments from me. The first is the result of John von Neumann, Newman maybe. In 1930s, he proved that any compact operator on a separable Hilbert space admits a proper closed invariant subspace. So he basically solved ISP for compact operators on a Hilbert space. And by the way, when I say a separable Hilbert space, I mean infinite dimensional. The finite dimensional case already resolved
Yes.
in the 19th century. So let's say it. H is a separable Hilbert space. T is compact. Then E admits proper closed E invariant subspace. The next result, which was published, these results were not published anywhere, and it has an interesting story behind it. I'll come to this later. The first published result on these matters is another paper by John von Neumann.
And why you call him Newman? It was Neumann.
And how should Neumann?
Yes,
Okay.
in all the Russian books, he's Neyman. And even they deprive him of his font from egalitarian reasons, maybe. But Germans, they say Neumann. Okay.
Then let
sorry.
me excuse my English. So the John von Neumann published 3 papers during 1929 and 1932, where he gave a full description of normal operators on separable Hilbert space. It's basically the spectral theorem, and an easy consequence of the spectral theorem that any normal operator admits an invariant subspace. Okay, let me copy this. E is normal. E. And let me copy this. Let's move on. Then there is a gap in this history because of the Second World War, but the mathematics revived on 1945. These are results by, let me get, Aronsian and Smith. They learned from von Neumann that any compact operator on a separable Hilbert space admits a T-invariant subspace. They didn't see the proof by von Neumann, and they come up with their own proof. So it's just the same result, but with official publication. Then in 1966, we have a new result. This result by Bernstein and Robinson. And Robinson. They showed that any polynomially compact operator on a separable Hilbert space admits yada, yada, yada. The generalization here is that we do not require the operator to be compact. We require to be compact some polynomial function of this operator. So in a sense, it's a generalization. And this generalization were achieved via very difficult techniques. These guys used non-standard analysis and the ingenious idea of embedding infinite dimensional Hilbert space into so-called hyperfinite dimensional Hilbert space. It's a crazy technique. A few people understood that proof, but later in 1966, Halmos came up with a simpler proof. He based his paper on the ideas of Bernstein and Robinson, but his proofs were much shorter and simpler. So let me again write the full statement. So T is a bounded operator. There exists a polynomial such that P of T is compact. And in this case, we solve the ISP.
P is non-zero, of course.
Yeah. So let me add Halmos here too. He proved that he gave this simpler solution the same year. Then in 1973, we had a small sensation. This a celebrated result by Lomonosov.
Victor.
Victor Lomonosov generalized most of the known results on ISP with his very unusual proof that involved fixed point theorem, basically nonlinear functional analysis. So his theorem looks like this. Suppose we have a complex Banach space. Then suppose we have a non-scalar continuous operator on E. Not, let me remember, non-scalar.
Lambda E identity.
Then suppose that T commutes with a non-zero compact operator K.
At least one, yes.
Then T has an invariant subspace, a proper closed invariant subspace, and even more, this subspace is shared with all operators that commute with K.
I remember this sensation.
as a common proper closed invariant space with all operators S that commute with K. Such closed invariant subspace is sometimes called hyperinvariant. The same year, another mathematician, American mathematician Hilden, saw this proof and just in 2 days came up with an even simpler solution. He gave an elementary proof of this result, which does not involve even the Schauder fixed point theorem. So basically, you can give this proof to the undergraduate students. And if we have time today, I'll try to show this proof. Then in 1976, Per Энфло published his breakthrough. He showed that there exists a complex Banach space and a continuous linear operator without proper closed invariant subspaces. So he showed that ISP, the answer to the ISP is negative for some situations. There exists a complex Banach space, a bounded linear operator, such that T has no. This paper has a long story, by the way, because the first version of this paper was too sketchy and basically no one wanted to read it. Then, after a few years of struggle, Энфло gave up and published a 100-page long detailed proof of his result. And the actual this long version was submitted in 1981. So it took 5 years for Энфло to give a detailed proof of the same result. And after fixing a few mistakes, he finally officially published his result in 1987. So basically 11 years from the sketch to the actual proof. Right now, specialists think that today's proof of the ISP would have the same fate. So Энфло just kickstarts his journey to the actual proof. Now, let's move to the 1980. By this moment, the mathematical community thought that the result of Lomonosov could be extended to arbitrary operators. So maybe Lomonosov proof works for all operators, and then it would be quite nice
Solution.
To have a structured theorem for operators on Hilbert spaces. They believe that all operators on Hilbert spaces admit such a compact operator with commutes with T. But bad news came in 1980. So Hadwin, maybe Hadwin, Nordgren, and one more Indian mathematician, Radyavi, and of course Rodenthal. So they gave an example of a bounded linear operator on a separable Hilbert space, which does not commute with any non-zero compact operator. This means that Lomonosov result cannot be extended to all operators on H. So let me write it down.
Rajavi is not Indian, right?
Oh, well, really?
Yeah, Rajavi is an Azeri guy. I mean, originally from Iran.
Yes.
It's unacceptable.
Then my sources were lying. Excuse me.
It's okay.
So the formulation is like that. H is a separable Hilbert space. T, there exists a bounded linear operator T, such that for any compact K,
They are not commute.
they do not commute. Okay, so the next 10 years were devoted to construction of different counterexamples to ISP. And this, by the way, were the time where most of the mathematical community knew that the counterexample exists, but officially it was not published. And it started a new race to publish newer and simpler results. For example, in 1983, Edmond gave an example of a nuclear Frechet space E and an operator T without proper closed invariant subspace.
So it is Frechet and what?
A nuclear Frechet space.
Nuclear Frechet, huh?
And an operator T such that T has no As far as I know, this construction uses a projective limit of Hilbert spaces. So basically, this space F is a projective limit of Hilbert spaces, and T is a right shift operator.
Oh.
Then in 1984, Charles Reed published his example of a negative solution of ISP. And many mathematicians in the community regarded that like a bad move because everybody knew that Enflo was the first to give the example, but officially his result was not published. Meanwhile, Charles Reed published it. His example were inspired by the ideas of Enflo, but his proof was simpler and shorter. And his proof, by the way, gave an example of a bad operator without invariant subspaces on L1.
L1.
Okay, I don't know if I have enough time to give. Okay, let me give a short construction of this operator. So the construction goes as follows. Suppose that P, the idea of the proof. Suppose that P is a space, is a linear space of polynomials in one variable. Now we choose a specific basis in F, in P. The construction is really involved and difficult, but this a very specific basis based on rapidly increasing sequences. Maybe someone of our visitors of the seminar remember CTEC giving a talk about the Argyros counterexample. This example also used rapidly increasing sequences to build weird bases. And this idea comes from Enflo's proof also. So this sum basis of P, and now we take any polynomial in P and represent it in this basis via some coefficients. And the norm is defined like L1 norm. Now we take the completion of this space. Of P with this new norm. The desired linear operator is basically a right shift operator. Note that the right shift operator worked as a counterexample also in Edmond's proof. So this was the shortest proof for a shortest counterexample to ISP, but then another mathematician, Bosmi, I don't know how to pronounce his name, Bosmi, maybe.
Bosmi, yes.
Oh, okay. He gave also a simpler proof for the same statement. In 1988, Reed gave an even stronger counterexample. He showed that there is a bounded linear operator on L1 such that the orbit of any vector is dense in L1. Note that we do not take the linear span here. Just the orbit of the vector is dense. Such vectors are called hypercyclic. And probably this closed the question of ISP on arbitrary Banach spaces. This result showed that the situation is dire. Then we had a quiet decade, or maybe even 2 decades. And the next interesting result came from non-Archimedean functional analysis.
Wow.
Excuse me, Sliva. He showed that any infinite dimensional Banach space of countable type over non-Archimedean field admits a bounded linear operator without proper closed invariant subspace. So basically, almost every Banach space in non-Archimedean theory admits a bad operator.
Yeah.
So we consider Banach space over field K. K is non-Archimedean.
Archimedean. Misprint. Not Ara. Oh, well,
for any such Banach space, there exists a continuous operator T such that T has no. The same year, Argyros and Hayden gave an example, gave a solution to the compact plus scalar problem. And from their construction, it follows that there are Banach spaces where every continuous operator has a proper closed invariant subspace. So in the realm of Banach spaces, we have really bad spaces like L1 and very good spaces where every operator can expect a structural theorem.
Yeah. So index loses sense for their spaces.
Poor theory. The construction by Argyros and Hayden, in their construction, that Banach space is a pre-dual of L1, which is interesting because the L1 itself gives the source of bad examples.
Yes, and there are many pre-dual spaces for L1, yes?
Yeah, a lot.
It is not C naught, of course, their space.
Then we come to this day, and this year, in May 2023, we have a new result by Enflo, which claims that any separable Hilbert space, any operator, any continuous linear operator on a separable Hilbert space admits a proper closed invariant subspace. By the way, the months later, another mathematician, Neville, published a proof with the same result. So just with a difference in 1 month, we have two proofs for ISP.
But are they checked?
No, both papers are not peer-reviewed, and that's the reason you need to stay skeptical. But I'll give a short overview of their proofs. Enflo. For any separable Hilbert space. and any continuous operator T, T has proper closed invariant subspace. The idea of the proof may sound simple, but the technicalities are crazy as usual in his proofs. The idea is that you take a cyclic vector and modify it in a such way that you iteratively modify this cyclic vector so that he becomes more and more uncyclic. And then after you take a weak limit of these iterations, you get a non-cyclic vector. So basically you get a proper closed cyclic subspace. Let me write it down. We assume that T is injective, because if it is not, then its kernel is invariant subspace. Also, we assume that this operator has dense range. And even more, we assume that for any non-zero vector y, yt is dense. In his construction, Enfloo shows that any such subspace, any such vector can be modified to get a proper closed subspace yt. That's all I can say about this proof, because the rest are just a lot of technicalities, estimates, inequalities, and also I watched a talk of Bogachev. He said that he looked through that proof too, and it seems convincing, but there are a lot of words like small enough, big enough. So there is no detailed estimates for that enoughs in the proof. That's what makes this paper difficult to follow. Now, let's proceed.
Vladimir Bogachev, you mean?
Yeah, Vladimir Bogachev. And a new, lesser known result I don't know if it's true or not, but this paper claims the same, that ISP, the answer to ISP is affirmative. But the proof is very different, and that proof is based on a lot of different results from maybe 80s even.
Which are true and checked.
Let's think so, because these older results are already published. So this proof is based on work of many mathematicians. The first result that this proof uses is as follows. The result is by Apostol, Berkovi, Poyash, and Piercy. By the way, this guy knows a lot about ISP. It's basically his career. So what does this guy prove? Do this guy prove? To give, well, I will not state the exact statement, but what they did, they studied specific subspaces of the Bergman space. The Bergman space is defined as follows. These are holomorphic functions on the unit disk with the norm f, defined as follows. It's just an integral with respect to the Lebesgue measure, but we take this measure, we normalize it. We divide by p, this measure. So this is the Bergman space, and there is a specific class of spaces here, which I call Z invariant. So we say that the space is Z invariant if the following inclusion holds. And these guys in 1985 gave description of such subspaces. The next result used is by Hedenman, Richter, and Sape. These guys showed that the ISP is equivalent to the following statement. For any two Z invariant subspaces in the Bergman space, suppose we have two Z invariant subspaces in the Bergman space such that V1 is contained inside V3. Then suppose that there is a big difference between these subspaces. So the quotient space is infinite dimensional. Now, if there exists another Z invariant subspace V2, between this V1 and V3, then we can give an affirmative answer to ISP. So basically, if you want to prove ISP, you need to prove this result.
No, it's sufficient. Yes.
So the idea of Neville was to show that this is indeed true. There was an attempt to prove this earlier, but it failed. And Neville claims that he finally found a simple proof for that. His proof is based on a theory developed by Neville. And this theory basically classifies the Bergman space, slices the Bergman space into subspaces of functions with specific order of zeros at a chosen point. Suppose you have this unit disk, you fix any point inside it, and you consider functions that vanish at this point. Since these functions are analytic, you can speak of the order of zero at this point. And you can consider subspaces with different order of zero. And miraculously, this trick works, and it allows to slice not the Bergman space, but even any Z-invariant subspace into smaller subspaces. And in his proof, Neville just adds to V1 one more dimension and shows that intermediate subspace V2 does exist. So basically in his proof, V2 is just V1 plus one specific vector X. If someone wants to read the proof, I would recommend to read this one because it's much simpler. It's closer to ideas of our seminar. This guy even employs Hilbert modules.
Oh,
So maybe next time someone tell us the details of his theory and his proof.
okay.
So what Enflo's proof and Neville's proof is correct? What are the benefits for us? As I said in the beginning, the main benefit that we can get a structural theorem or bounded linear operators. At this moment, since we know we are not sure that this proof is correct, we have no deep insights from this proof because of all these limitations. At the moment, we can claim only that any bounded linear operator is triangulizable. In the beginning of the talk, I described what generalized triangular form mean, and if Enflo's proof is correct, we can expect that any bounded linear operator can be represented in this form. As for the unsolved problems, I have two, one for optimists and one for pessimists. If we recall the history of the question, we can see that all counterexamples come from non-reflexive spaces. So maybe the ISP has an affirmative answer for all reflexive spaces, not just the Hilbert space. So if you believe that Enflo is right, then the next question, can this proof be extended to all reflexive Banach spaces? So the question is, any T, he has proper closed invariant subspace. And for pessimists, if Enflo is not correct and there is a counterexample, the next, not if Enflo is not correct. Suppose again that Enflo is right, but what about hyper invariant subsets? proper closed invariant subset. That's the whole history I wanted to tell you. Now I have 15 minutes, right?
You have whatever you want.
Oh, well, then I can give a quick proof of the Lomonosov-Hilden theorem. I mean, this result that was considered a big breakthrough back then. So the Lomonosov-Hilden theorem. It says that every compact operator other than 0 has a non-trivial hyper-invariant subspace. Let's start. That's the theorem. And that's the proof. Let K be a compact operator on a complex Banach space X. We know that K has eigenvectors. Well, it might, if K is quasi-nilpotent, then it doesn't have eigenvectors, and this will be the main case of the proof. If K has eigenvectors, then these eigen subspaces immediately become hyperinvariant. So from now on, we can assume that K, the only point in the spectrum of K, is 0. Eigenvector X. Suppose K has an eigenvector X, not 0. Then we have a hyperinvariant subspace. This subspace will be a proper closed invariant subspace, not only for K, but for any operator that commutes with K. So from now on, we assume that the spectrum of K is 0. From the spectral radius formula, we know that the norm of any power of K tends to 0. Even more, this holds true for any constant C, or any complex number C.
Of course.
Let's move on. Without loss of generality, we can assume that K has norm 1. We can always scale K, and it doesn't change any invariant subspaces. Let's pick some vector x naught such that norm of K, K applied to x naught, is greater than 1. Also, let B denote the closed unit ball at x naught. of radius 1. Clearly, 0 does not belong to B. Why so? Because K has norm 1. No, X not. That's excuse me. Is not in B. That's it. Then 0 does not belong to the closure of the ball, of the image of the ball B. Also. From now on, let's consider a family of subspaces My, where Y is an arbitrary vector inside X. These subspaces are defined like images of Y under all possible bounded operators A that commute with K. Clearly, the identity operator commutes with K. So Y always belongs to My. And as a consequence, if Y is not 0, then My is not a 0 subspace. That's good. One can easily show that My is a linear subspace which is hyper-invariant. But we don't know if the closure of My is a proper subspace. So now our goal is to give an example of the space My whose closure is not the whole space X. My is not dense in X. Let's define an interesting set UA, where A is a bounded operator that commutes with K. UA is the pre-image of the ball B that we discussed earlier. This is the ball around X naught of radius 1. A careful gazing shows that the union of such sets let me think. We take the union of the sets over all operators A that commute with K, not all possible, but those that commute with K. And we get the whole space X without 0. That's the construction. Now, consider the closure of the image of B under K. This is a compact set because K is a compact operator. And this set is contained in X without 0 vector. Because of the compactness, now we have an open cover of this compact set. And hence, we can extract a finite subcover. Basically, we can extract a finite number of operators that commute with k, such that KB, the closure KB, is contained in this union. What else? The main point that the construction so far is the same as in the Lomonosov's paper. And the difference between the Lomonosov's proof and Hilden's proof starts only at this point. Lomonosov uses fixed point theorem to get his result, while Hilden uses a so-called ping-pong technique. So let's see what the technique does. Consider vector x naught, the center of the ball B. Clearly, k of x naught is inside k of B. Nothing special here. But what does it mean? It means that k x naught is contained in some set UA for some number I1. Okay, what does it mean? By construction of this set, it means that A with the number I1 applied to the vector k x naught is inside the ball B. Well, then it means that k applied to this construction AI1 kx naught lies inside KB. Nothing smart here. But again, we can recall that we have this kind of cover. Hence, k AI1 kx naught lies in some set U of AI2, for some number AI2. And we can keep this ping-pong technique as long as it takes. In the end, what do we get? We get that for any number m, we have the following chain: im minus 1 applied to k, etc. AI1 kx naught lies inside the ball B for some numbers, natural numbers I1, etc. Im. Now, consider a constant c, c, which is the maximum of all norms of the operators here. Recall that we can consider only n operators that come from the compactness property. So this quantity is finite, that's okay. And the inclusion here can be modified. Let me copy this and sprinkle with constants. Let's add a constant c minus 1 here, c minus 1 here, c minus 1 here, and all operators k are moved here. K to the power m, c to the power m applied to x naught. One may question, how come I can change order of the operators here? Simply because I consider only operators that commute with k. so I can move k wherever I want. Now recall that by construction, all these operators, including the constant, they have norms at most 1. And also, by our choice of operator k, we know that this norm tends to 0. So if we take a limit here, when m tends to infinity, we basically get that 0 belongs to B. But by construction, 0 is not in the ball B. That's the contradiction. This contradiction arrives from our assumption that my is dense in X. Hence, for some vector y, contradiction. Hence, for some vector y, the closure of the space my is not the whole space X. Hence, my is a proper closed hyper-invariant subspace. That's it.
Excellent. So you have finished.
Yeah, that is all, I think.
Thank you very much. So what are questions?
You're welcome.
Yes, questions, comments. I have only, I was present once when I was in England, and Charles Reed was there. Charles Reed was extremely, as you know from what Norbert says, a capable person, and also very nice gentleman. But at that moment, he thought that he has proved that in Hilbert space there are invariant subspaces, what we discussed. And and then he wanted to go to Mexico for swimming. And imagine that just one day before he was to leave, he found mistake. And everybody of us was, of course, very disappointed with it. Just to entertain you a little bit. Unfortunately, now he is not with us. He died unexpectedly. No, already many years passed, but very, very nice person. So excuse me for this interruption. So maybe there are other questions? No. No, so again, we are very thankful for Norbert for a very interesting and educated talk, and we shall see what will happen with Enflo fruit. So far, Enflo was right, everybody, in everything what he does.